So looking at this class, there's a few people that's behind a couple of things. Like there's still a few that haven't taken part 2 of the last test. Some of you have, and I haven't graded it yet because if you turned it in over the weekend, I saw there's some things turned in over the weekend that I have not yet graded, but I will be getting to that and get that in the grade book. But I had everything updated up to the end of last week when I left. I just haven't done any grading today because I've had classes all morning, but I will get an update. But I see a lot of grades moving in the right direction here. See a lot of grades moving up, and like I said, I usually see that during the matrix portion of our semester. I'll see things going in the right direction. So the matrix assignments just seem to be a little easier to understand or something. For some reason, people turn those in and raise their grades, which is awesome. So if you're behind on any of these matrix assignments, get those going, get those turned in. And, we're going to wrap up matrices this week. So we're still missing a dozen people in here. Everybody must really be piling in the lunch or something. So anyone got any big plans on spring break? If not, you can come over and help me clean out my garage. Okay, that wouldn't be a very exciting spring break, I don't think. I've done a few cruises. Love cruising. So we've done a cruise in the Caribbean. We went to like
Sorry, my
Cozumel and
belly
all
button
that.
wouldn't go away, but it's going to the Bahamas.
Oh, a Bahamas cruise. Ah, nice. Yeah, I've been to like Jamaica and Grand Cayman and Cozumel on a cruise, and I've also been to Alaska on a cruise, and I've been up the St. Lawrence River in Canada and ended up in like Boston on a cruise. So I've kind of cruised all around the U.S. The only things left is next year we might do a Hawaiian cruise because I haven't done that direction yet. So next year, my wife and I are celebrating 40 years of being married. Our 40th is next year, so we're planning a big trip. We just hadn't decided where the big trip's going to be, but Hawaii is definitely in the running for that. But spring break cruise, I'm jealous. I've done a cruise. Two of the cruises we did was during the summer, and one was at Christmas, which is pretty wild. All right, well, it's 12:50. We're going to go ahead and get started, and anyone who's late is just going to have to be late. That's why I record this, because some folks are like going to miss it altogether because they're eating a lot of dessert with their lunch or something. I don't know why. But, all right, let's put this up on the screen and see what shows up here. We go to the grade screen, as usual. Let's see, this was Module 5 that we finished back in February. Then we've been working through matrices. So as long as you don't have anything over here that says it's missing, if you see a due date, there should be a submitted date next to it. Due date, submitted date, due date, submitted date. So we get down here. We're down to week 28, and we have a quiz. But I think we do have a lesson to look at before the quiz. So don't just jump right into the quiz. Let's look at the lessons today. See what's in the week 28 folder. So just anything that's in the week 28 folder. Matrices. We do. We have the properties of matrix addition and scalar multiplication. So there's a folder that has, 3 different lessons in here. So let's look at these. And then the quiz is this week's assignment. So let's start right here. Intro to zero matrices. Because you really got to understand what a zero matrix is and how that kind of affects things. Because I know there's a quiz problem that deals with that. All right. Let's see if we can. A little bigger. It may be too big. All right, let's go here. Again, it reviews what a matrix is right off the bat. It's a rectangular arrangement of numbers as rows and columns. So this is a 2 by 3 because the rows go before the columns. 2 by 3 matrix. And it has some links to some of the past lessons if you've forgotten any of that. But let's define what a zero matrix is. This shouldn't be too surprising. A zero matrix is a matrix in which all of the entries are 0. Here's a couple of examples. This is a 3 by 3 zero matrix. Look, we generally call it O. We call them A and B, and we give them letters. So we really have an O or a 0. This is a 3 by 3 zero matrix, and it has 3 rows and 3 columns of zeros. A 2 by 4 zero matrix, 2 rows and 4 columns of all zeros. So a zero matrix is indicated by this O, and a subscript can be added to indicate the dimensions if necessary. So zero matrices play a similar role in operations with matrices as the number 0 does with real numbers. Let's take a look. What happens when we add a zero matrix? Now recall, when we add 2 matrices, we just add the entries together. If you need a refresher on how that works, remember, if we have this 2 by 2 and this 2 by 2, you just take 3 and 5 and add those together, because those are both at the first row, first column. Take the 7 and 2 and add those together, 2 and 8. You end up with 8, 9, 10, 5. Remember, the big thing about addition and subtraction is these have to be the same size. If that's a 2 by 2, this has to be a 2 by 2. And the answer will be a 2 by 2. That all works together. So that's just a review on how matrix addition works. So let's look at this with a zero matrix. 4, 5, 1, 3. Okay, that's our first matrix. And then we're adding this zero matrix to it. So when we add 0 to this matrix, this should not be a surprise that the answer is 4, 5, 1, 3. Because when we add 4 plus 0, 5 plus 0, 1 plus 0, 3 plus 0, nothing changes, right? Check. That should not be a big surprise, right? Because we know how to add 0. We've known that since we were wee little bitty folks. How about this one? What if we have a 0 first? And I'm taking the 0 and I'm adding this matrix to it. So I'm adding 0 plus -2. Well, still, we know that 2 plus 0 and 0 plus 2 is the same thing. So 0 plus -2 is going to be -2, 0 plus 3, 0, 0 plus 4, 0 plus 8, -1, and 7. Anytime you add 0 to something, you just get something. Check. Hopefully you won't need the help, but there's how it works. 0 plus -2, 0 plus 4, 0 plus -1. Yeah. So in conclusion about zero matrices, when you add an m by n zero matrix to any m by n matrix A, you get matrix A. A plus the 0 matrix is A, or 0 plus A is A. The dimensions of the 0 matrix are not explicitly given. It is just understood that it has to match matrix A, because they have to be the same size. Even if it's a 0 matrix, it has to be the same size. So here's a reflection question. If we have matrix B right here, what are the dimensions of the 0 matrix that we can add to it to get B? All right, you can put that in the chat then. Put in the chat, what are the dimensions of the 0 matrix that we can legally add to matrix B? And there's matrix B. Yeah, the only one that we're allowed to add to it would be a 2 by 3. Yeah, great job. Check. Has to be the same size. And since this is a 2 by 3, the 0 matrix has to be a 2 by 3. All right, what happens when we add opposite matrices? Like if we have matrix A and we want to add matrix -A. Well, if this is A, then -A would be exactly the same numbers, but the opposite signs. Since this is a 4, this is a -4. This is a 1, this is a -1. -6, +6, +2, -2. Nothing changes in the numbers. The only thing that happens is we multiply everything by -1. So what would happen if we add this matrix to its opposite matrix? What would you expect to get as the solution? What would the sum be? Yeah, we take, just like we add any matrices, we take 4 and we add -4. We take -3 and we add 3. We would get a 0 matrix. And it would be a 2 by 2 because these are both 2 by 2s. So if we add opposite matrices, we end up with a 0 matrix. Very good. Ooh, what if it's bigger? What if it's a 2 by 3? Oh, this has got to be different, right? Now we're going to add -4 to 4 and 2 to -2 and 5 to, it makes no difference, right? We just get a bigger 0 matrix. That's the only difference, is that our 0 matrix is bigger because it has to match the size that these other ones are. So again, a lot of this is kind of like, well, duh, Mr. Barack, of course. Yes. And I want you to understand it that well, that this does seem like, you're kidding me, Mr. Barack. This seems a little silly. Yes, unless you don't understand it, then it doesn't seem silly. It seems very confusing. But don't make this confusing, because it really is that simple. If we have a matrix and we add its negative matrix, it ends up all zeros. Or if the negative matrix is first, it doesn't matter. We add up all zeros. Or if we subtract a matrix from itself, if we have A minus A, we're going to get a 0 matrix. Because it works just like in math. 4 minus 4 is 0. How about when we multiply by a scalar of 0? Remember, when we multiply, we just take whatever number is out front, the scalar, and multiply it by everything inside the matrix, 2 times everything. We end up with a matrix that's twice as big, right? All those numbers are twice the size of the original. Well, just the same principle applies here. If we multiply all of these numbers times 0, we get zeros. Even if it's bigger, still we can multiply 0 times everything. It's a 0 matrix. It's just has to be the same size. The answer has to be the same size as what you multiplied by here. Scalar times this is that. So in conclusion, when you multiply any matrix by the scalar 0, you get 0. And if we want to compare a 0 matrix to a real number 0, like with, right there. So with the number 0, if we have A can be any number, and we add 0 to it, we end up with A. 9 plus 0 is 9. -3 plus 0 is -3. Same thing with a matrix. Matrix A plus 0 is the same as 0 plus matrix A, and it just equals matrix A. It is that simple. Adding any number to its opposite will give 0. 6 plus -6, 0. -11 plus 11, 0. Doesn't matter. Same thing with a matrix. A plus a negative A is going to be a 0 matrix. And any number times 0 is 0. 4,812 times 0 is 0. Well, any matrix times the scalar 0 is a 0 matrix. All right, so that's not too bad. Like, okay, I like this 0 matrices, Mr. Brock. It's pretty simple. Yes, it is. Let's look at the next lesson. Properties of matrix addition. Let's talk about how matrix addition works. Okay, we're going to look at these properties that have to do with addition. The commutative property, which basically says, and this is of addition, the commutative property of addition, it says A plus B equals B plus A. Like, sure. In math, we say, 1 plus 3 is the same thing as 3 plus 1. Right? Either way, it's 4. A plus B equals B plus A. That works with matrices just like it works with regular numbers. Same thing. The associative property. A plus B plus C. We can add B and C together first. If you got 1 plus 2 plus 3, and we want to add 2 and 3 together first, okay, 1 plus 5, we're going to get 6. But if we say, no, if I have 1 plus 2 plus 3, I'm going to add 1 and 2 together first. So I've got 3, and 3 plus 3 is 6. It doesn't matter. If you're adding 3 numbers together, you can add whichever 2 you want to first before you add the third one. And the same way with matrices. Add any of the 2 matrices together, and then add the third one. And it doesn't matter which order you go in. Okay, the additive identity property. It says for any matrix, there is a unique matrix 0 such that A plus 0 equals A. So if you show me a matrix, I can show you that there is a unique 0 matrix that I can add to it and get the original A. If it's a 2 by 2 matrix, I can add a 2 by 2 0. If it's a 1 by 5 matrix, I can add a 1 by 5 0 matrix. If it's an 8 by 2, I can add an 8 by 2 0 matrix and get your original matrix. That's what that's saying. I can match it with whatever size you got. And the additive inverse, the opposite. For every matrix A, there's a negative A that I can add to it and get a 0 matrix. Absolutely. I'll just take all the same numbers you've got. I'll change the signs on all the numbers, and we'll get a 0 matrix. And here's the closure property. And what the closure property means, if I have A and I'm adding B to it, the answer is going to be the same size as A and B. If I take a 2 by 3 matrix and I add it to another 2 by 3 matrix, the closure property says the answer is going to be a 2 by 3 matrix guaranteed. There's no way it can be anything different. 2 by 3 plus a 2 by 3 cannot equal a 4 by 9. It has to equal a 2 by 3. That's what the closure property says. All right. Let's explore. Tells us again what a matrix is. To add 2 matrices, we just add the numbers together. It's just reviewing there. It says, okay, now let's talk about dimension considerations. The sum of 2 matrices that are 2 by 2 is another 2 by 2 matrix. That's the closure property. You can't get something that's the wrong size. And if the dimensions of the 2 matrices are not the same, look, we've got a 2 by 3 and a 2 by 2, cannot be done. This is undefined. Undefined. There's no answer if they're not the same size. Okay, let's talk about matrix addition and real number addition. So the commutative property says matrix A plus matrix B is the same as matrix B plus matrix A. Just like 3 plus 5 is the same thing as 5 plus 3. It doesn't matter. Either way, get you the same answer. So with the matrix property, if we have these 2 matrices, we can take the first terms and add them together as 3 plus 5, or I can reverse that as 5 plus 3. These are the same. 3 plus 5 and 5 plus 3 is the same thing. Which means if we break this back apart, we can put the 5 first and the 3 second. Here we had the 3 first and 5 second. See, this took matrix A and moved it to be second. Matrix B is now first because this is the same thing as this. So since those equal the same thing, we can swap these around. A and B can trade places. A plus B equals B plus A. That's the commutative property. All right, let's look at the associative property. So the associative property says if I'm adding 3 numbers together, 2 plus 3 plus 5, I can add these together first. All right, I can add the 2 by 3 together first and then add 5 to it. So it'd be 5 plus 5, that equals 10. But I can take those same three numbers and I can add these together first. 3 plus 5 is 8, but if I add 2 to it, I still get 10. So this is the same as this. It doesn't make any difference at all which ones you add together if we're adding three numbers together. That's the exact same for matrices. If I have A plus B plus C, well, here's matrix A, here's matrix B, here's matrix C. I can add A and B together first before I add to C. 5 plus 3 plus 1. So that first term would be 9. Where over here I said, look, I'm going to add B and C together first. So this would be 5 plus 3 plus 1. So 5 plus 3, it's still 9. Does not matter which order we add together first, just like in actual numbers. All right. The additive identity property. We can add a zero matrix to a matrix and we still get the same matrix. Nothing changes. When a zero matrix is added to matrix A, the result is always matrix A. 2 by 2 added to a zero matrix. 2 by 3 added to a zero matrix. It doesn't matter. We end up with the same as what we have in matrix A. The additive inverse, that's where we take the opposite matrix. So if we have this as matrix A, we can take the opposite. -2, +2, +8, -8, same numbers. And when we add them to one another, there's the two matrices. Those numbers all zero out. We end up with a zero matrix. Additive inverse. Inverse means opposite. So if you hear additive inverse property, oh, that means they're opposites of each other. Inverses. All right, here's our practice problems. A, B, and C are all 2 by 2 matrices. 2 by 2. So if we have A plus B plus C, and we're adding A and B together first, which of these are the same thing? Which of this will give us the same answer? In this case, we're going to add A and B together, and then we're going to add C to it. So which of these will give us the same result? Ethan says, I think it's the first three, all three of these. What do you think? Vivian can agree with that. Well, a property that we looked at told us that AB plus C is the same as A plus B plus C. So that's what our property told us for sure is exactly the same. But we didn't talk about adding C and A together. Can we add this one and this one together first and then bring B in afterwards? Yeah, absolutely. It doesn't make a difference. And this is just like, well, it's just the same as adding the three together, however you do it. Yes. The reason this doesn't work is C is being added twice. This is A plus B plus C plus C. You got C twice. You get two C's. So that is not the same. Check. Absolutely correct. Great job. All right. Ooh, I might have to make this a little smaller to see it all. Which of the following are equivalent to A plus negative A, and that's in parentheses, plus B, and they're all 2 by 2s. A plus a negative A plus B. Which of those below are equivalent? And these are all 2 by 2 matrices. All right. Vivian's looked at it again and kind of updated her answer. So we know that if we add A and negative A together, they'll just end up a zero matrix. And if we add a zero matrix to B, it should just be B because the zero matrix plus B. And this is C is adding a zero matrix to B, which is what we would get if we add these two together, right? That would give us a zero matrix. And since B is a 2 by 2, D is not possible because B is a 2 by 2. So this is not possible. But what about this? This is saying we would add negative A to the B first and then add that to A. And that would be the same thing as doing this. Yeah, that's the property we just looked at. It doesn't matter. We got three things adding together. It doesn't matter which ones we add together first. B is, so I think we're at the same thing. A, B, and C again. Very nice. All right, that's the end of that lesson. Properties of matrix scalar multiplication. All right, scalar multiplication. Let's look at these properties. So here's all the properties. I'm going to make it a little bigger. I don't want to go up the screen now. We're going to look at the associative property, which says if we have two scalars, C and D, being multiplied by this matrix, we can multiply C and D together first. 2 times 3 times a matrix, right? We can say 6. Or this says we can multiply one of the scalars, take D and multiply it times the matrix, and then multiply that result by C. And that's the same thing. So this basically saying if you have three things to multiply together, it doesn't matter which order we multiply them in. That's true. 2 times 3 times 4. If we do 2 times 3, that's 6, times 4 is 24. But 2 times 3 times 4, let's take 3 times 4 together. Well, that's 12 times 2. Well, that's still 24. It doesn't matter. These are the same. The distributive property. We use the distributive property a lot. When you have something outside the parentheses, you have to multiply it by everything inside the parentheses. So if we have C times A plus B, that's the same as CA plus CB, because that's how it works. That makes sense. But this is saying you can also take two scalars, C plus D, and multiply them times A is outside the parentheses. So we can distribute the A to everything inside the parentheses. So that works as well. Whether we have two matrices inside the parentheses or two scalars, either way, we can just distribute what's outside times both of those. Multiplicative identity property. Okay. It's a little different than the additive identity. The additive identity was saying we was just adding zero. It's the same. In order to get the same thing when multiplying, we have to multiply times 1. So remember the additive property, the additive identity property, additive said if we take A plus 0, that would get us back what we started with. That works with addition, right? That works with addition. But with multiplication, you multiply by 1. Identity property means you end up with the same identity you started with. Over here, you end up with the same identity you started with. 1 times A, multiplicative. Okay. Multiplicative properties of 0. 0 times A is 0, or a scalar times the 0 matrix would also be a 0. So if the scalar is 0 or the matrix is 0, either way, you're going to end up with a 0 matrix. And the closure of property. The closure property multiplication says a scalar times a matrix will be a matrix that has the same dimensions as the matrix started. So if this is a scalar times a 3 by 2 matrix, the answer is going to be a 3 by 2 matrix. If it's a scalar times a 1 by 5 matrix, the answer is going to be a 1 by 5 matrix. The closure property just says that whatever you end up with is going to be the same size as what you started with. So let's explore these a little bit more. All right, so this talks about scalar multiplication. Just to remind you how that works. 2 times a matrix was that, which we looked at before. A scalar times a 2 by 2 matrix is a 2 by 2 matrix. That's what we mean by the closure property. It has to be the same size, is what it starts. So let's look at each property individually. The associative property, which says we can multiply two scalars together, then a matrix, or we can multiply one by the matrix, then by the other scalar. So let's look at this. For C equals 2, D equals 3, and we have this matrix A. So that's what we're going to start with. So we could take the two scalars, 2 and 3, and multiply them together, and then times each element. So 2 times 3 is 6 times 5. That would give us 30. 2 times 3 times 5. Or we could take the 3 and multiply it by the matrix first. So 3 times 5 is right there. And then multiply it by the other scalar, 2 times 3 times 5. So this would be 2 times 15. Well, 2 times 15 is 30, just like 6 times 5 was 30. It doesn't matter. We can do it either way. You're multiplying those three together. Pick which ones you want to multiply together first, and then do the other one. You'll get the same answer. A distributive. Scalar. Got two matrices in the parentheses. It's going to equal the scalar times the first matrix plus the scalar times the second matrix. Here we have a scalar of 2, and we have two matrices. So when we take the 2, here, 2 times, we can add those matrices together first, 5 plus 3, and then take it times the 2. So that's 16. Or in this case, we went and distributed it and said 2 times this matrix plus 2 times this matrix. So that would be 2 times 5 is 10. 2 times 2, oh, that's the second one over there. 2 times 5 is 10 plus the 2 times 3. 10 plus 6, also 16. You'll get the same number either way. This looks at the other way. If we had two scalars with a matrix outside the parentheses, C plus D, the same numbers here, 2 and 3, and as we had on a different problem earlier. So we could take the 2 plus 3 first, would be 5 times 6 is 30. Or we can distribute the matrix. 2 times this matrix plus 3 times this matrix. 2 times 6 plus 3 times 6. 12 plus 18 is 30, just like it was when we did it this way. 30. The multiplicative identity property. 1 times a matrix equals a matrix. 1 times 2517 equals 2517. Because you're just multiplying everything by 1. I think we can understand that. Multiplicative properties of 0. 0 times any matrix is a 0 matrix. 0 times 3867 equals 0, 0, 0, 0. Starts as a 2 by 2, ends as a 2 by 2. You're just multiplying 0 times each number in the matrix. And again, if we were using a 0 matrix with any scalar, 3 times a 0 matrix. 3 times 0, 3 times 0, 3 times 0. We end up still with a 0 matrix just like we started with. All right, check our understanding. Here's our questions. Which of the following are equivalent to this? We've got a few things going on. We've got 1 times A in the parentheses, then it's being added to B, and then we're multiplying it times a scalar C. Wow, so what is equivalent to this? You bet, Piper. Okay. So people are saying this is equivalent and this is equivalent. So let's break it down. 1A means we're multiplying A by 1, which means it's just A, right? Just A. Nothing changes there. So let's see. So that would mean it's just like C times A plus B. Because 1A simplifies to just A because it's multiplied by itself. And then here, this is the distributive property, which we know equals that, CA plus CB. And we also know that if you add these two together, we can reverse it and add it the other way. It's the same thing. That's the 3 plus 5 equals 5 plus 3 principle. This has a problem here because it's missing a C. It didn't distribute properly, right? If you distributed the C, they would both be multiplied. So this one doesn't work. Good job. Absolutely correct. All right, let's try this. I think this is our last problem. It is. Which of the following are equivalent to, we've got two scalars being multiplied together, and then being multiplied times matrix A, and then we've got a zero matrix being multiplied by matrix A, and then we're adding all that together. Wow, CDA plus 0A. Wow, what all applies there? So this is which of these are equivalent. That's going to take a little bit of working through there. We can simplify a few things.
Okay, so we've got arc length or the circumference, and then we've got like this core measurement. So the 17 plus 17 is going to.
So Ethan's got B and C on there. Thinks it's this one and this one. So let's see, how do we get like this one? This is like working backwards. Like we can factor out an A. There's an A there and an A there. So if we factor the A out, what's left when you factor it? You get CD plus 0. So that's working backwards, which is CD plus 0 times A. So yeah, that certainly should work because we factored out an A. What about this one? Well, 0A is just a zero matrix. It's just a zero matrix. And if we add a zero matrix to this, we just get this because this goes away. And this is multiplying C and D together first, then times A. This is multiplying D and A, that's C, but those are equivalent. Very good. But A, let's look at the top one. This is a zero matrix, so it goes away. C and D times A would not equal just A unless these multiplied together to be 1, right? 1 times A would be A. But this is C and D. Those two numbers would have to multiply together to be 1, which means they both have to be 1, right? So I don't think that works. So A can't work. Let's check. Oh, we're correct. All right. And that is the third lesson. So let's look at the quiz. There's a problem on here, I think, that giving some people some fits. Oh, here it is right off the bat. Do I have this doing random order? I think I do. I like this problem. If A, B, and C are 4 by 4 matrices, and 0 is a 4 by 4 zero matrix, which of the following is false? Okay, that's what's going to get you. Pay attention. Which is the following is false? If they're 4 by 4s and O is so there's a 0 there, there's an O matrix. So you got to go through those very carefully to figure out what is false. Does AB equal BA? Does ABC equal A times BC? Some of these don't even use all the matrices. Like 0, the 0 matrix is not used in this one and this one or this one. So don't even worry about the 0 part. Just figure if these are all 4 by 4 matrices, is this true? Does A times B plus C equal AB plus AC? That's just going back to the properties we just looked at. Are those the same thing? I want to look at number 2 here. This is real interesting. A, B, and C are all either identity or zero matrices. Like, wait a minute, I don't understand what you're saying. They're either identity or zero matrices. Right. If it's a zero matrix, you're just figuring, okay, I'm just multiplying times 0. If it's an identity matrix, since these are multiplying, see, A times this matrix, B times this matrix. See, A, B, and C are matrices. There's a matrix. So this is actually multiplying 6 matrices together. 6, and it equals this. An identity multiplies by 1. So it wants to know, to end up with this answer, A, B, and C, some of those are 0 and some of those are 1. Which ones? Would it work if I said, let's see, this one is an identity matrix, so it's multiplying by 1. This one is a 0 matrix, so it multiplies by 0, and this is a 1 identity matrix. Which of the matrices must be identity? Oh, apparently there's only one. Only one of them is an identity. So 2 of these would have to be a 0 or something. Oh, no, wait. I can check more than one answer. That's not true. I can check more than one answer. So there can be more than one. There can be more than one. But which ones would have to remain? If it's a 0 matrix, then that one disappears, right? I would just be putting this. Oh, that's a minus. Minus this. This one minus this. Would that equal that? So that's what you're looking at. If it's a 0 matrix, if I said A was a 0 matrix, that means this one goes away. It's just zeros. So I'd be taking B minus C. So look at all the possibilities. If I made this a 0 matrix, that means both of these would be identity matrix. I would check C and B if that's true. Both of these are identity matrices. Identity matrices. All right. If A and B are 2 by 2 matrices and C is a scalar, based on the properties of scalar multiplication and addition, which of the following are equivalent to this? So you got to figure out which of those are identical to this. All right. And there's only 4 questions. If X is a scalar, this is a scalar, and you have this problem, this times this equals this, what is X equal to? If it's a scalar, it's just a number, it's not a matrix. It equals 1, or it equals 4, or it equals 41, or whatever. But it does not equal a matrix because X is a scalar. But that's our assignment for this week. 4 questions. It's our final quiz on matrices. We're going to move on to something else. Final quiz on matrices. And it uses all these properties like, okay, identity property means I'm multiplying it by 1. So I get to keep that matrix. If it's a 0 matrix, that matrix goes away. There's a lot of logic. It's like a logic puzzle this week because you got to step through those carefully and piece by piece and say, does that work? Does that work? So take your time on this. This could be not difficult, just tricky if you rush through it because you got to think about each of the steps of what that means with the parentheses, associative property, distributive property, all the fancy math terms. But that's it, guys. Do your best. If you're missing any of the matrix work, get all that done because we're going to move on from matrices next week. So this is your chance to get caught up on anything before spring break because next week we'll have 1 lesson to be done for spring break. Which, by the way, next week there's no school on Friday. You get spring break a day earlier, Friday through the whole next week, starting next week. So this week is our last in-person Friday before spring break because we don't have school next Friday. Virtual lab is still open Wednesdays and Thursdays if you want to come up and get help. Both weeks, Wednesday, Thursday. And our party is this Friday from 1 to 3. Going to come up for our spring party up here in room 1600. We'll be doing that Friday afternoon. So have a great week. We'll catch you guys next time.